Hello, everyone, and welcome to my talk on linear algebra and GPU computing. My name is Itai Segev. I'm a senior kernel developer here at Wolfram Research. I wear several different hats at the company. Today, I'm wearing the hat of guy who's good at building across different platforms, and so I'll be talking to you about integration of linear algebra into some numerical libraries. So my plan of attack is to briefly review the basics of computer linear algebra, then outline the current work and the motivation for it, give you some live examples, and then some performance data of why we care about this sort of thing, and then talk about future directions. So it's interesting. Charles, in his talk introducing a GPU array, gave a little history, and I'm also going to give you a history, although it turns out to be a completely different history, even though we're both talking about the same thing. So just to make sure we're all on the same page, I'm going to start at the very beginning. So commonly, we talk about the two sizes of real numbers, singles or floats, which are 32 bits. And I have all the details there, but we don't need to worry about all the details. And then doubles, which are 64 bits or 8 bytes. And that gives you a number that's the largest number, that's about 10 to the 308. Notice that the difference between 32 bits and 64 bits is quite a difference in order of magnitude. You only get up to 2 to the 38. So I'm going to ignore other sizes. There are quads, there are half floats, which are not widely implemented or not standardized. And I would say they're not particularly relevant to sort of pure linear algebra because, if you go to 16 bits, you have much fewer digits, much smaller numbers. The condition number, if you know what that is, can build up quite quickly. And yeah, it's hard to do linear algebra. So modern CPUs natively support both floats and doubles. So if you're operating on a single pair of numbers, operations are completed equally fast. That's what it means to sort of natively support them. This changes when you use vector instructions, which allow the same operation to be applied to many pairs at once. Now, if your numbers are half the size, you can fit twice as many of them into the same space, and so you get roughly the performance. I mean, there are issues around cache sizes and memory transfers and blah blah blah. But if you do the graph, which I have done in the past, then you do see that it is pretty close to twice the performance. And obviously, matrix operations have a lot of you dot things. You're multiplying and adding a bunch of numbers, doing the same operations. So there are two key standards for software standards for linear algebra. One is BLAS, which provides basic operations such as dot products and multiplication. And the other is LAPACK, which is built on top of BLAS and provides solvers, decompositions, and other things. And there are many implementations of each standards. There's the original one. They're from hardware vendors. There are others. I'll briefly mention some of those things. So what is GPU computing? So what a GPU unit does, what the graphics processing unit does has changed over the years and probably still changing. But the current thing we call a GPU traces its origin to 3D accelerators of the late 90s. And they focused on parallel computing and were optimized for linear algebra operations like rotations and translations because they wanted to, move a sprite around the screen. Eventually, adding special effects allowed the running an arbitrary program, which we typically call a kernel these days, on each pixel. So this made it possible to do general computing on the GPU, which could be faster in some cases. Right, so except for a small number of optimized operations, it's quite slow compared to the CPU, but it can do it simultaneously on thousands of data points. So what was originally implemented was single precision and less, and even today there are graphics cards that only do single precision and less. That's going to be important. In 2007, NVIDIA introduced CUDA, which is a software standard for doing sort of general computation on the GPU. And then other standards followed, like OpenCL, HIP or ROCm for AMD GPUs, Direct Compute on Windows, Metal Compute for Apple platforms. So just very quickly about BLAS. It started as a Fortran library in 1979, and it's divided into 3 levels of vector-vector, matrix-vector, and matrix-matrix. And it has wonderfully intuitive names like S dot, single precision dot product, or perhaps my favorite, Baxby, double precision, A goes to AX plus Y. So it's AXPY. Yeah, I can't remember these names, and I've discovered even some of our linear algebra experts can't remember all these names, so that made me feel a little bit better when I was doing this. So some implementations, again, there's the original implementation. Apple has an implementation called Accelerate. It's CPU only, so that's going to be important. Intel has the math kernel library, which has CPU plus some GPU support. There's OpenBLAS, which is a cross-platform CPU library. There's CUBLAS, which comes from NVIDIA and is part of the CUDA toolkit. And ROCBLAS is AMD's equivalent thereof. So what's LAPACK? LAPACK started about a decade later and is built on top of BLAS, and it can solve linear systems, do least squares, eigendecompositions, SVD, and related things. And it has similarly intuitive names, which I will not go into. So some of these functions are driver functions, which solve a whole problem like eigendecomposition. Others solve specific parts using specific algorithms, like you could do do a partial LU decomposition and then whatever, then do some least squares or linear solving based on that LU decomposition. So again, if we look at implementations, we have a lot of the same implementations. We have the original one. We have Apple Accelerate, which again, CPU only. We have Intel's MKL. We have OpenBLAS. We have ROC Solver, which is for AMD and is a self-described work in progress. So I have not dived deeply into how much is there yet, but that certainly suggests that it's not complete yet. NVIDIA chose not to implement LAPACK, but instead created its own library called CU Solver with the intent of providing the useful LAPACK-like features. So this provides a lot, certainly not all, but a lot of the same functionality as LAPACK, but using different function names and naming conventions. Okay, so why did I tell you all this history? Well, that's to explain how I'm approaching GPU array linear algebra support for GPU array. So right now I'm focusing on CUDA. As Charles mentioned in his talk, if you attended it, right now we have CUDA working and some support for Apple. But Apple's Accelerate is CPU only, so it's not really going to be very helpful in doing GPU linear algebra. So CUDA provides us with the core libraries we need to implement, do efficient implementations of higher level functions like linear solve and singular value decomposition, etc. Another benefit of doing CUDA, which is that we have CUDALink, and I guess I should have also mentioned CUDA compiler tools, which Charles mentioned both of these. So this allowed us to exploit the Wolfram compiler. I did not have to write a single line of C or C++ code. I had to look at some headers because in order to hook up our code to the CUDA libraries, I needed, certain, number values to match up or whatever. But basically all the code I wrote to make this possible was Wolfram language code. And then the Wolfram compiler building on top of CUDALink and CUDA-compile tools did all of the hard work of, generating object code, and if you know what NVCC is, running NVCC, et cetera, et cetera. Okay. All right, so I've talked about this, about what we can do. Let me show you something in action. So I'm going to start with a very simple example. So, and I guess I forgot to delete the outputs, but I will run these so you can see that these things really are live. I've created a GPU array from the CPU. It's from the data on the CPU. It's real 64. It has dimensions 2, 2. We see a couple of data points. I can do the same for the GPU, and I can then call linear solve, and I get out a solution X, and I can verify that this is a solution. And actually, just to make clear that this is all happening on the GPU, right? So mGPU.x, so dot happened on the GPU, and then it was tested for equality on the GPU, and lo and behold, they match. Now, for this very simple input, the solution is identical to the CPU solution. That's obviously not going to be the case for general things. And the other thing is to notice in this input is the automatic transfer back to the CPU. So, I did linear solve here of mCPU, vCPU, right? That's going to be, in fact, if I do an evaluate in place, voila, there's the information, there's the normal list. Now, when I said X is a GPU array, I'm subtracting a normal array from a GPU array. What to do? Well, we take the data from the CPU back to from the GPU back to the CPU, and then do normal arithmetic on it. So that was my first example. Here's my second example. So now I'm going to take the same data, but I'm going to first convert it to real 32 or floats. And I do the same thing for the vector, and I can linear solve that, and lo and behold, it's a 32-bit solution, or a 32-bit reals solution. It's still a solution, but now it's not going to be equal to the CPU solution, because we only have 32 bits, so we have some round-off error. In fact, we have really tiny round-off error because it's such a simple solution, right? 32 bits gives us about 8 digits, and we got about 15 digits of accuracy. So that's just luck. That's not going to happen in general. So singular value decomposition. Let's recreate our GPU array, and now do the singular value decomposition. The singular value decomposition gives us 3 matrices, 2 rotation matrices, and the matrix of singular values. We can reconfirm the decomposition by dotting those 3 matrices and making sure it equals the original matrix, and indeed it is. Now, the singular values are the same, or very, at this point, identical, but certainly very similar to, because they have to be. The rotation matrices are not the same, and they don't have to be, right? Because we can choose different normalizations, different phases, et cetera, et cetera. So, some entries are the same, others are not. That's just okay. The decomposition is still confirmed. So now for singular value decomposition, we will add I to each entry. So we'll have a matrix of complex reals, i.e. Complex doubles is what I meant to say. And look what happens when we do the SVD. We get 2 complex matrices. Those are the rotation matrices. And we get a real matrix, because the singular values are going to be real, or in fact, we know they're non-negative. And so we get the matching real type, right? This is a complex of two real 64s. The singular values are therefore real 64. We can still confirm the decomposition. Entries are more different because we have more phases, et cetera, to choose from when we have complex numbers. And we see, you know, it really is solving it on the CPU. We get a tiny little difference in the first singular value, but, you know, it's basically right. All right, so why do we care? So now I'm going to show you some plots generated on 3 different computers where I compared doing linear solve, and I specified to do the direct method just to sort of make the testing as similar. I mean, that's probably what linear solve would have chosen to do on its own, but just to be on the safe side, I explicitly specified the method just to be sort of as similar between the CPU and the GPU. And then I compared that to linear solve. So I generated random near diagonal data in square matrices of dimensions which are multiples of 1024, and then sort of compared these. And so one plot shows the speed up you get using real 64 on the GPU versus the CPU, and the other shows real 32. And so here I'm using a very high-end card, about $1,500, $1,600 cards versus 2 Xeons. These are actually relatively low-end Xeons, so this is maybe $1,300 worth of CPUs here. And you can see with doubles, we get some speed up, you know, maybe factor 75%, 100%. That's a little something, but nothing to write home about. If we do the computation on real 32, well, we can get up to a factor of 60. So yeah, that's quite a speed up, and that's because, you know, these GPUs, they natively support reals. They quote unquote support real 64s, but it's just not the same. So on the second computer, it had a Threadripper. This was roughly a $3,000 CPU when it was released about 4 years ago, against a 4080, which is about a $1,000 card. And we see we do get some speed up with doubles, but it's much less. But we still get a nice speed up, obviously not as dramatic a speed up, but still a nice speed up using floats. And then this is my home computer, and the one that I'm using right at this instant. So I have an RTX 4060, which is roughly a $300 graphics card, versus my Xeon W7 3445, which is a roughly $2,500 CPU. And you can see the speed up is a factor of 1/2, i.e. it is slower to do this on the GPU than the CPU when you have real 64s. You know, right there, we have this little pike right at this size here, which I'm not sure what that's about. I presume it has something to do with sort of optimal memory sizes or cache sizes, but we have it at both of them. But, you know, we get a much more modest speed up, you know, maybe a factor of 7 or so. But, you know, considering $300 versus $2,500, you know, that's not bad. The other thing I want to point out in these slides is notice how the x-axis is getting shorter, right? If we're going to do things on the GPU, then the array needs to fit on the GPU. You know, on the CPU, you might have, you know, tens, if not hundreds of gigabytes of RAMs. You know, I believe that the 4090 has 24 gigs of RAM. You know, my $300 4060 has 8 gigs of RAM. You know, that's a lot less than you might, you know, even my MacBook Pro has 64 gigs of RAM. That's a lot more than the 8 gigabytes on an RTX 4060. So you're sort of more limited in the sizes of problems you can deal with. In the future, could we think about, well, we split it up and, but now you're transferring a lot of data back and forth. It's not clear what, that there will still be a benefit at the end of the day, or how much of a benefit there will be. So that's one potential downside to GPU computing. So what's currently working? So arithmetic, dot, transpose, linear solve, singular value decomposition. Linear solve has some issues that I need to fix, but as you can see, it's working. Sort of the next couple of things I would like to tackle are eigensystem and least squares. In longer term, additional decompositions and dealing with the consistency requirements. And I will sort of explain what I mean by that. Well, that's referring to this bullet point here, and I will explain both of these bullet points in better detail on my next slide. And obviously, as we add support for more architectures, we'll assess what linear algebra. Right now, like I said, Apple doesn't even give us basic BLAS. I'm not going to by myself write a BLAS library from scratch. That would take a long time, even if I had the background to do it, which is not really what I do. So we'll have to see if there are other libraries we can use, etc. So about consistency. So consider this problem. We take a GPU array matrix which of real 64s, and then we take a vector of real 32s, and now we do linear solve on these two inputs. So what should happen here? Should we convert the vector to real 64s? Should we convert the matrix to real 32? Should we return unevaluated because this is an error? Should we move the data back to the CPU and proceed to something else? I'm not sure what something else is, but there might be. And there isn't an obvious answer, and I would say there are probably different opinions within the team about what to do. What we do right now, which I think is a good sort of default, is we take the data back to the CPU and do normal evaluation. So you at least get a result. I think that's sort of the most user-friendly thing. We might make ways to make this sort of more customizable. Well, again, that's something we haven't thought. A similar thing, I think probably a bit, a similar thing exists for, say, adding matrices and vectors. So, right, Mathematica, you can add a matrix and a vector and they thread. I mean, I think we pretty much all agree that that's probably what should happen if you do two GPU arrays, but that's not the native behavior of these libraries, and so that just doesn't work. I think we're pretty much all in agreement. Well, this is Mathematica or Wolfram Language. We should have the Wolfram Language behavior. There are a lot of things that need to happen to make this a really polished feature, which haven't happened yet. So it remains work in progress. So in conclusion, using the GPU can significantly speed up linear algebra computations. It doesn't necessarily. We've made significant progress and there's more to come. I'm missing the semicolon right there. I would like to thank the Wolfram compiler team for lots of help, because this was sort of my first project really exploiting the full potential of the Wolfram compiler, and I had a lot of questions. I know my slides aren't up. I sent them in last night, but the people in charge for putting up the link told me that for some reason they couldn't add the link until after the talk happened. I don't know why that is, but look for the slides on to come up later. I have a bonus slide with bonus examples if you want to dig into them or ask questions about them. But right now, I will pause to see if there are any questions I can answer for you. Right, so I see there's one question. Is a list of GPU arrays that are currently supported available somewhere? I don't think we have sort of an explicit list, but certainly in any modern, any reasonably modern, say 5 years or less, GPU should be supported. So certainly in our 6000 ADA should be supported. Assuming you have an up-to-date CUDA toolkit installed, then then that should just work. I believe you need compute level 8. Don't quote me on that. But that's several generations old in order to support these. Right, so there's a question here of, is this the total contribution of all cores, and is this potentially impacted by the standard number of cores of a typical Mathematica license? And the answer to that question, no, that is not impacted by licensing, because what licensing restricts is how many sort of main threads, how many evaluators can be running. And when we do these deep numerical linear algebra things, then we're having a single computation that exploits the low-level library, and that low-level library, which in this case is MKL, because I'm running these on Intel machines with Linux, it will decide how to distribute the work among the cores. So I can tell you, having done the profiling and knowing that it was in fact using all 20 of my cores, and so yeah, so I was getting the full benefit, and this was not in any way restricted by Mathematica licensing. Right, so, and then there's finally a question about there were particular dimensions that got much bigger speed up, and what caused that? And so the short answer is I can't tell you for all of them. For some of them, it sort of has to do with exactly, how the memory is aligned, or, sort of are you just small enough that basically almost all the computations fit in the cache, and so they're much faster, or have you gone just past that, and so now you need to rely less on the CPU cache and use more memory reads. So I can explain some of them in terms of, it has to do with exactly how the problem fit in the memory of the CPU or the GPU, but I certainly can't explain all of them. Right, on my plots of GPU, CPU, does a dimension 32,768 mean matrices of 32 by 768 or vectors? Well, the short answer is yes, right? So my matrix is 32,768 by 32,768, and I'm doing a linear solve on giving it a vector input of, right? So the A matrix, if you will, is 32,768 by 32,768, and the B matrix is 32,768, and we're solving A dot X equals B. Is GPU computing for mid-sized problems small enough to fit and large enough to be worth the transfer? Let me try to read that again. Is GPU computing for mid-sized problems small enough to fit and large enough to be worth the transfer? Okay, I understand the question now. That's certainly the case where you get the most benefit. People, have done work with very large problems where, they split it up, and then each piece, and they sort of minimize the number of transfers, et cetera, et cetera. or they sort of split it up into independent pieces and send each piece to its own GPU and then combine the results later. Charles talked about we would love to support multi-GPU and these sorts of hybrid problems. That's most of the time when people do it, they write their own code, their own C or C++ code that they compile for their specific machine. Automating that is a hard problem. It's certainly something we want to tackle, but I'm not going to sit here and promise you that because, like I said, it's a hard problem. Don't think I see any other questions. I'm surveying the list of questions here, and I think I saw them. I think I've answered them all. So thank you very much for your attention, and have a good rest of your conference.